Welcome back, Lecture 11. We have a couple topics to finish from Section 2.3, and we'll get a 2.4 and maybe 2.5 today, part of, all of. The goal is to get somewhere in 2.5 today. We'll be very close to where we should be on the syllabus. We are looking at the possibility of a kind of a low-grade hurricane hitting us later today and tomorrow. From what I read and what I hear, the one that is coming next is going to pack a great deal more punch than the one that's coming tonight and tomorrow. So I think tonight is Hannah. You know, it kind of sounds like Hannah's just kind of barely going to creep in, and, you know, nobody will pay much attention to Hannah. But Ike, I think Ike is going to pack a punch, and I don't know about the other one. We're actually looking at another one. Ike, does that, okay, I know what you're laughing at, Eric, but I'm not going to say that. But then we have another one coming, Josephine. So we've got a series of hurricanes. NC State does have an adverse weather policy. I'm saying that to you guys that are here in the classroom. So just pay attention to that. If it is such that I can't make it to campus, which we had a bad one in 96, Fran in 96, I literally could not get out of my neighborhood with major trees down everywhere. Then if I have electricity, I'm going to try to email you to tell you not to come to class. But if it's that bad, you're probably not going to come anyway. But just pay attention to the adverse weather plan, because I think we have the possibility of having some adverse weather here in the next week. All right, let's wrap this up in limits, some kind of special situations in limits. We had a lot of them yesterday. In general, if you can substitute in, if x is approaching 3 and there's not an issue with plugging in 3, use direct substitution. If direct substitution doesn't work, we've got to have some other plans. Some of these problems that we do as examples in here, they are also examples in the book. Those are normally the kind of, I don't know, I call them classic examples, some of the better teaching examples. As much as possible, I try not to use the ones in the book. You can read those. I'll try to use other problems that are similar or have different things happening that we need to be prepared for as well. But sometimes they're kind of classic problems. This is a so-called kind of classic problem. So we want to know what happens on this function, absolute value of x over x as x approaches 0. What we might want to do is take a look at this in pieces. Let's come in from the two different sides. Come in from the right side of 0 and from the left side of 0. When would the absolute value of x be exactly the same thing as x? When it's positive. So if we're dealing with the positives, what's the quotient of the absolute value of x divided by x? It's 1. 0 is kind of a bad value. We have to stay away from that, because 0 would give us 0 over 0, which we can't write anything down there. What about when x is negative? What's the absolute value of a negative number over that negative number? That's negative 1. So this graph looks something like this. Does that make sense based on what we just decided? Positives, you get 1. Negatives, you get negative 1. 0, we can't plot anything. So let's look at this in pieces. What about as we come in from the right? What's the limit? 1. And in fact, it is 1, right? Again, we don't care what happens when x is 0. We care what happens as x approaches 0. So it's 1. It's stuck at 1. And how about coming into 0 from the left? Negative 1. Good. So the fact that we got two different answers here says that what is the answer up here? Great. See, you people don't need me here. I'll just kind of show up just to make it official. Does not exist, okay? Or no limit. Okay, questions on that before I move it? Let's take this function. How many of you have dealt with that function before? Does that look familiar to anybody? If I give it a name, maybe that'll help. The greatest integer function? Have you had that before? Some of you recognize that name. Yeah, I'm writing fast today. I know. That's why I'm saying what it is first, so I'll kind of translate it for you. But I'm trying to get us back where we should be, but I'm hearing you on that. My script is not the best in the world. Greatest integer function. So when we put a number in there, let's say 3.7. This is not a rounding now. We're not rounding up. Basically, it's a truncation formula. So what's the greatest integer that is in 3.7? Would be 3. We're not quite to 4 yet. So no matter how far we get in the 3s, 3.8, 3.9, 3.99, if we're not to 4, then the greatest integer in that number is 3. The greatest integer in 3.999 is 3. So if you graph this, it looks like a step function is what it looks like. I won't graph all of it. But the greatest integer in a half is 0. The greatest integer in 3/4 is 0, because we're not to the integer 1 yet, so we have to go back to the preceding integer. Greatest integer in 0 itself is 0, so all these is 0 till we get to 1. The greatest integer in 1 is 1. Greatest integer in 1.2 is 1, 1.4 is 1, 1.9 is 1, all the way till we get to 2. The greatest integer in 2 is 2. And it keeps going that way. So we get this step function is what the greatest integer looks like when you picture it. That becomes an issue when you're taking a limit, especially at the integer values. So let's just say 3, since we kind of started with that number anyway. Let's do this in pieces. So in the top one, we're going to put in numbers larger than 3. Is that correct? 3.1, 3.01. They're getting close to 3, but they're larger than 3. And since they're larger than 3, what's the greatest integer in all these numbers? It's 3. Because we're already to 3, even though they're just a little bit above 3, they're still larger than 3. These values right here are a little smaller than 3. 2.99, 2.999. They're getting close to 3, but they're not to 3 yet. What's the greatest integer in all these numbers? 2. That'd be 2. So, because we get different answers, the answer to what's happening as x approaches 3 does not exist. Very good. Now, keep in mind that just because the function is, changing drastically at integer values, that if you're not in an integer value, it can still have a limit. So if we had same function, this can have a limit because we're not at one of those places where it jumps up or jumps down. So at 3.8, we can approach 3.8 from both sides, and in both cases we get what for the answer? 3. So it's the function is, how we do the limit problem is somewhat related to where we are on the graph. If it's at one of the integer values, transition takes place there, we have to pay attention. If we're not at an integer value, no transition takes place. We just kind of plug it in and see what happens. All right, last thing that, actually let me not use script here. Thank you for the reminder. Another thing about me using cursive is that if my spelling is bad, you probably can't tell because you can't read it anyway. So, but now I'm kind of, my spelling is being called into question, that I have to do something else other than cursive. Squeeze theorem. So let's say that we have, let me draw a little picture first and then we'll do one example. Let's say that we have this value out here, a, that we're approaching. And we know that some function up here dips all around and does this. And some other function does this. And we know some other function, yet a third function, is basically bounded between these two functions. So it's doing this over here, but it's always in between these two. Well, if the other two have a limit as x approaches a, and that limit is the same number, wouldn't it make sense that the one that's sandwiched between these two would, in fact, have the same limit? So that's pretty appropriately named the squeeze theorem. So if we know that, let's just give these names. Here's the f of x. Here's the h of x. And we know that this g of x is always in between the other two. And these two on either side, this has a limit as x approaches a. This also has the same limit as x approaches a. Well, then it doesn't leave much of a decision for the one that's between the other two. It must also have the same limit. So if they're converging on a certain number, I don't know, let's give it a name here, call it capital L. If they're both converging on capital L as x approaches a, then for goodness sakes, the one that's in between the other two must converge on capital L as x approaches a. That's not a very formal definition or formal picture of the squeeze theorem, but the gist of what it is accomplishing, I think, is accomplished in that picture. So if this has a limit, capital L, this one has a limit, capital L, as x approaches a, this could be the strangest function you've ever seen, but if it's bounded by these two, it has that same limit. Speaking of strange functions, there is one in the book, and this is one that is slightly different. We can accomplish a couple things with this example. We've got to have trig. We've got to have our daily dose of trig, so there's a guarantee that we're having trig today. See, that's exciting. Saw your faces light up on that one.
Is that a 4?
That's a 4. Cosine of 4 over x. And one of the first things that I would think about when I saw this is that x is approaching 0 and we're dividing by x. Well, we're okay as long as x is never exactly 0. So don't let that throw you off. And in fact, 4 over x shouldn't throw you off either. What should catch your attention, and maybe not on this problem, but subsequent problems that you see that are similar to this, is not the 4 over x, not the division by x, but that we have the cosine of something. Think about a cosine graph. I don't care what it is. So we're kind of disregarding the 4 over x. The cosine of something is bounded between what two values? No, what two? I'm sorry, I didn't make that clear. The two y values. 1 and -1, right? So this can be a strange graph, but it's going to be somehow bounded between 1 and -1. Why? Because it's a cosine. It's the cosine of something. You're never going to get larger than 1. You're never going to get smaller than -1 for the cosine of something. Now, some cosine graphs go above that and below that, but they have a lead coefficient, right? Like a 4 cosine or an 11 cosine. This is just cosine, cosine of something. It's somewhere between -1 and 1. So is it true that this function, the one in question, is somewhere between -x squared and positive x squared? Is that correct? Because this piece right here is somewhere between 1 and -1. So at its lowest, it's going to be -1. -1 times x squared is right here. At its largest, it's going to be +1. +1 times x squared is right here. So let's look at these two outer functions. Why? Because the one in the middle is kind of hideous looking. So let's look at this one. What happens there? Let's look at this one. What happens there? And I think basically we'll be able to answer the one in the middle by what happens to the two on the outside. What about -x squared as x approaches 0?
That would be 0.
0. What about x squared as x approaches 0? That's 0. So the limit here is 0. The limit here is 0. Even though the one in the middle is kind of ridiculous looking, because the two on the outside are approaching 0 as x approaches 0, what's the answer to this?
0.
It's also 0. So there is an example of the squeeze theorem. So we kind of look at what might be an upper bound, what might be a lower bound. This is always in between those two. They both approach 0. Therefore, the one in the middle has to approach 0. So we can sometimes steer clear of pretty ugly functions with the use of the squeeze theorem. All right, kind of hard to separate the ideas of limits and continuity. So that is the next section, and it flows perfectly because you have to talk about limits in order to decide if something is continuous or not. So let's go into section 2.4. How do we determine if a function is continuous? Thankfully, there are whole classes of functions that are continuous. Polynomials are continuous everywhere. That's why they're usually the first types of problems we look at. They're easier, they're smooth curves, they don't have any jumps or infinite discontinuities, no discontinuities at all. But if we have suspicion that a function is continuous at a certain value, we need a way to check it to see if it is. So we're checking for continuity at an individual x value. So at x equals 3 or x equals 5, how do you know where to check it? You check it where you think it might be discontinuous, where it's suspect. We're not going to be able to check every value, but we only need to check the ones that kind of are possibly in doubt. It's a 3-part test. We'll do the kind of the mathematical sentence, and then we'll do this question we ask ourselves to actually get past that particular step. So here's the question. The f of a exists. Okay, that little question mark, have I explained that? You were talking, some of you were talking about Spanish before class. Spanish was my minor in undergrad. The thing I love about the Spanish language is if you know it's a question when you start to read it, because they've got this little symbol to start the phrase. So does the f of a exist? That's the question we're asking ourselves. Another way you can say that is there a point plotted there? If there's not a point plotted there, guess what? It's discontinuous, okay? Then we would be done. So at any point in time where it fails, if it fails at test number 1, it's discontinuous. If it fails at part number 2, it's discontinuous. Even if it passes part 1 and part 2 but fails at part 3, then it's also discontinuous. If it makes it through all 3, then the only way it could do that is for it to be continuous. Nicole.
If there's the points are open circles, which I guess would be like a hole, is it still continuous on that line, even though
It's not continuous there.
not continuous?
Well, I've got an example that I think will clarify that. If there's an open circle and there's no other point plotted in that vertical line, it's discontinuous there. One way of thinking about continuity, without trying to get cute here, I've had people get cute on this particular topic in the past, so you're not allowed to get cute, is if you can draw the picture without lifting your pencil from the paper, probably it's continuous. Now here's what I mean about being cute, which is not allowed. Okay, that's got an open circle there. I drew it without lifting the pen from the paper, but in reality, when we talk about an open circle, there's really just a gap there, right? So I would be drawing along, and then I'd have to skip over to here, right? We use that open circle to, amplify the fact that there's not a point there. But that's discontinuous just the same as this is discontinuous. So drawing it without lifting your pencil from the paper, we probably need something a little better than that. So that's what this is. Here's test 1. F of A exists. Is there a point plotted there when X is A? If there's not, it's discontinuous. Part 2. Does it have a limit? So as we get close to A, are we getting closer and closer to the same value? If not, then it's discontinuous. Does it have a limit? See, this is the whole cursive thing. It's killing me. Does it have a limit? Now, luckily, part number 3, we've done the 2 parts that go together to make up part number 3. So if you know how to do the first test and the second test, basically, was your answer to number 1 the same as your answer to number 2? So is this limit that we have from part 2, is it the same as the point that was plotted from part 1? If that's true, there's no way this thing could be discontinuous. If the value we're approaching is the same value that's plotted, it's got to be continuous. So these are our 3 kind of tests or checks to see if a function is continuous. Does the f of a exist? If so, go on to test 2. Does it have a limit as x approaches a? If so, go on to 3. Basically, test 3 is compare your answer to number 1 to your answer to number 2. If they're the same, then it's continuous. So here's a picture that I think, Nicole, will have the situation that you brought up a minute ago. We're going to look at 3 different limit problems, 3 different continuity problems from this diagram. So let's look at what happens on this picture. Actually, what we're doing is this continuous? I'm a step ahead of the game here. Let's back off of that one. That's really number 2. Let's do number 1 first. So we're looking at this picture, a round the a value, the lowercase a. Is there a point plotted when x is a? No point is plotted, so we don't even need to do number 2. Okay? So not needed. No, there is no point plotted there. Therefore, it's what? Discontinuous at x equals a. That doesn't mean the whole thing is discontinuous, but it's discontinuous at x equal a. Now, if you're considering the function as a whole, is this function continuous? Well, the fact that it failed at a means that there's no way the whole thing could be continuous. Just showing some different situations on this diagram. Let's move over to B. Does the f of a, the f of, that's why I said the f of a. We already did a. F of b. Is there a point plotted when x takes on the value b?
Yes.
Yes, there is.
There is. So it's b something. What's that look like? Capital L? There is a point plotted there. Okay? Now, what do you think? Is this going to be continuous at x equal b? If you look at the picture, you know it's not going to be continuous because it's down here, and then just instantaneously after that, it's up here. There's no way it's continuous. But as far as test 1 is concerned, it's continuous. Okay, does it have a limit as we approach B from both sides? So we're approaching B from this direction and from this direction, both sides. Are we converging on the same value?
No.
We're not.
No.
Does not have a limit. So what's our conclusion? Is this continuous at x equal b? Not continuous. It failed test number 2. All right, let's see if I can, I know I'm getting cluttered here. Let's go up here. I want to keep the diagram here. Continuity at x equals c. Does it pass the first test?
Yes. Yes.
It does. There is a point plotted there. C something. N. So there's a point. Now, do you think it's going to be continuous at x equals c? It's not going to be continuous, but test 1, it passed. Does it have a limit?
No.
It does have a limit. Are we converging on the same value as we come in from both sides? Yes, we are.
Yeah.
So we're coming in here toward C. Are we getting closer and closer to the same value? Yes. What is that value? M. So here it's got to fail in part number 3 because we know it's discontinuous. So is the limit equal to the f of c? No. The
No,
limit,
it's not.
the value that we're approaching from both sides was capital M. The value that we actually plotted with some other value, that was capital N. So it's discontinuous. So you can have a lot of different ways that it can be discontinuous, and this doesn't even handle all of them. This just handles kind of how it could fail in the first case, how it could fail in the second case, and how it could get by the first 2, but yet still fail. We know for a fact that graphs do all kinds of crazy things that aren't necessarily on this picture. Infinite discontinuities, all kind of jump discontinuities. Some graphs, when we try to evaluate the limit, we can't even evaluate the limit from both sides because the graph doesn't even exist on one side. Here's an example. Let's say that we're looking at that. That's a pretty simple graph. You kind of have to talk about the continuity, but not continuous everywhere, because it doesn't even exist everywhere. What's this look like?
It's like half of the, I could go like cube.
Okay, kind of goes up there to the right. I get that shape. Half of a parabola, right? That's actually what it is. So it's the principal square root of x. If we did the negative square root of x, we'd have the bottom half to this parabola. It's not included in this set. So is it continuous everywhere? No. Is it continuous at 0? Well, you got to even be careful at 0, because it does exist. We do have a limit coming in from the right. Do we have a limit coming in from the left?
No.
We don't. There's nothing over there to the left. So this kind of has continuity in a sense, but not the same kind of continuity that's continuous everywhere. It's continuity at x equals 0, but from the right only. So there is such a thing as a left-hand continuity and a right-hand continuity. Here's an example of something that's continuous only from the right. Nicole.
And on the WebAssign, one of the problems was a chart like this. You had to show where it was continuous and discontinuous. The graph on the left side started at -4, and it was an open circle, so there wasn't a point there. But one of the options was negative infinity to -4. Since the graph started at -4, it wouldn't be continuous from negative infinity to -4, right?
From negative infinity
To
all the way up to -4. Do we even know what the graph is doing?
Not up until -4. Now
Okay.
it starts at
That's kind of hard to make a decision. Probably not a good WebAssign question if we don't even know what the graph's doing. Does anybody have that picture with them, what that looks like?
I can pull it
Anybody
up.
have a printout of it? Kelly, you want to bring it up? Okay. I know the thing doesn't like white paper. Does the start thing. So from the graph of G, state the intervals on which G is continuous. Select all that apply. Negative infinity to -4. That's kind of tough to make a decision on that. We don't even know where it is. It doesn't exist, so I would say it can't be continuous there, at least the part that we have pictured in red.
I didn't put them in, and I got it right, so.
Okay. Negative infinity to -4, not including -4. I don't think we know anything about that either, do we? From -4 to -2, including both endpoints.
No.
Okay. If we include both endpoints, I think it makes a little jump there at the end, doesn't it? It's up here, and then it jumps down to right here. -4 to -2, but we're not including -2. I think we're okay. So we're kind of ignoring that little jump that it takes at -2. So if you leave that out, then that part of the graph right there to the left of my finger is in fact continuous, right? But if you include -2, it's not continuous there. Is that okay? Does that answer that?
Yes.
Hopefully there's not a mistake in WebAssign there, but I don't think we can make a decision about it. There are other intervals, but I think that's the one that is her question. One of the things that is pictured here, pass that back to Kelly, thanks, is some infinite discontinuity. So if we have a picture, and I don't know that we've had an example quite like this yet, but it does happen occasionally where it goes infinitely discontinuous, but it heads toward positive infinity on both sides. That's clearly a break, right? Clearly discontinuous. So in fact, we actually give it a name. It's infinitely discontinuous there. I mean, doesn't that fail in the first checkpoint? There's not even a point plotted there, so it can't be continuous.
But would there be a limit that day? Just infinity?
Yeah, well, that's a good question. Okay, so let's tackle that. For descriptive purposes, I think it's okay to say in this case, that we're going to positive infinity on one side and positive infinity on the other side, is it descriptive to say that we're headed toward positive infinity? Yeah, there's some validity to that statement. Mathematically, that's not correct. What would the correct mathematical answer be? Does not exist, because it doesn't have a limit. A limit means it kind of converges on one specific number. This, to me, has always been limitless, right? It's unlimited. This is unlimited. It's going all the way to positive infinity. So this is used some, but that's really kind of for just descriptive purposes. The best answer, the best mathematical answer, is to say does not exist. A limit does not exist. Now, on a testing situation, obviously because the authors of this book use this and also this, I'll accept either one of those, but I'm kind of endorsing that answer. That's the best mathematical answer. Chandler.
Okay, so let's say you only have one side of that graph instead of the other side, and it goes from, let's say, point B all the way, and it's approaching A. Is that continuous? Or
Here's what I think you're saying. Tell me if I'm getting it right.
What would the interval be, I guess?
So are you talking about now a horizontal boundary?
No, a vertical boundary, just
Okay.
still the same. Let's say the graph starts at point.
So this is some A value.
Yeah, and it's starting at like A1, and it's.
Well, it can't be A1 because if that's a vertical
Oh
boundary.
no, asymptote. Just it starts at point A1.
Some here, some point here.
Some point
Okay.
there, and is approaching up through A into to positive infinity. And
Here.
Continues. Yes.
Okay. So if you're talking about being continuous right here at some other point, it is. It is continuous here because we're approaching the same value that gets plotted.
What about the starting point to A?
Okay. Is this continuous?
Yes.
Yeah. If this is included,
Yes.
so let's say that's R. So on the interval from R to A, now if we include A, it's not. But if you don't include A, it is. Right? That's a continuous curve.
So it would just be non-inclusive of A.
Right. As long as you stay away from A, that piece right there can be continuous.
Okay, that makes sense.
We could have a function that is continuous on an interval. Let me put this function up here. How many of you recognize what that is? Y equals, or f of x equals, square root of 4 minus x squared. Anybody recognize that?
Half circle.
Half circle. Okay, let's off to the side over here. If you did not recognize that as a half circle, what could we do with it so that you might recognize it as a half circle? Square both sides, which, by the way, is not necessarily the same set as what we started with, but we're messing with the equation. And if you bring the x squared over, that should look familiar, right? Circle, center at the origin, radius of 2. But if you go back to what we started with, we don't have the whole circle. Which portion do we have of it? The upper half. We want the principal square root. So we've got this set of points that is a semicircle. Is it continuous on that interval from -2 to 2? Yes. So it can be continuous on an interval, and in this case it would be that closed interval, right? Continuous on that closed interval. Doesn't even exist anywhere else. The authors in this section make a big deal about polynomials. It is a big deal. Polynomials are continuous everywhere. So what is a polynomial? something that looks like that. And in fact, it must be true that all of the exponents are, somebody tell me. What has to be true about all of the exponents in order for it to be a polynomial?
Positive.
They're going down.
What kind of numbers?
Positive.
Integers.
Integers. What kind of integers?
Positive.
Positive or in non-negative. Okay? The exponents are non-negative integers. If that's not true about that function, as simple as it might be, then it's not a polynomial. This isn't a bad function. It's not a real complicated function, but that's not a polynomial. So polynomials are continuous everywhere. And another thing about them that we'll appreciate as we get into the calculus and derivatives and where they exist and where they don't exist is that these are smooth curves as well. So all of the changes are fairly smooth in a sense that there aren't any corners or cusps or any abrupt changes in direction. So these are continuous everywhere. Rational functions, we see those a lot, they're continuous on their domain, which might sound a little funny. They're continuous where they actually exist. So if we have a rational function that looks like this, it doesn't exist at x equals 3. Is that correct?
Yeah.
Everybody agree with that?
Yes.
X can't be 3, and in fact, x equals 3 is a vertical asymptote, right?
Right.
Is this continuous everywhere else?
Yes.
Yes. That's the only bad value of this function. So this is continuous everywhere in its domain. 3 is not in the domain. So it is continuous at all values in the domain. X equals 3 is not in the domain. Y equals sine of x. Is that continuous everywhere? Can you think of a sine graph not existing somewhere? It's continuous everywhere, right?
Yes.
What about y equals cosine of x? Continuous everywhere?
Yep.
Okay, they're not polynomials, but they are continuous everywhere. But don't think that just because sine is continuous everywhere and cosine is continuous everywhere, that any combination of them, which tangent is,
What's it called? Pi over.
it's sine over cosine, which is the quotient of two continuous functions. Does that mean it is also continuous? No, tangent is not continuous. When you start dividing by things, you have to be aware that that denominator could possibly be 0, and in fact it is 0. Give me a value for which the cosine is 0.
Pi over 2.
Pi over 2, cosine of pi over 2 is 0, so the tangent doesn't exist there. So pi over 2 is not in its domain, but everywhere else it should be continuous, right? I mean, we've got some multiples of pi over 2. So a tangent graph looks something like this. So pi over 2, and then how far from there would it be discontinuous again?
Pi.
Pi, right? Tangent repeats every pi radians. So these are the problem areas. Pi over 2 plus
Pi.
integer multiples, right, of pi.
Yeah.
Is that correct?
Yeah.
Where n is an integer. capital Z is used for integers a lot. So these are the problem values. Pi over 2, find one of them, and then just say how far the others are away from it. Some integer multiple of pi, and then these are the so-called bad values for this function. It's
On both.
discontinuous at those places.
Is that on both negative and positive?
Yes. If n were negative 1, this would be pi over 2 minus pi, which is negative pi over 2, which is another discontinuity. So as long as you find one of them and you tell how to get to the others, that'll suffice. So this is where it's discontinuous. Let's finish with this one. This is about a 30-second problem. It's about what we have left. Got a denominator. We all kind of look at that denominator and say, we've got a bad value here. Possible. Is there any way this denominator could ever be 0? No. The worst this could be is what? I mean, aren't we somewhere between 1 and negative 1 here? So are we ever going to be 3 for the sine of x? No. So we're never going to get 0. So that takes that potential bad value and throws it out. Do you think there's a problem with letting x approach pi over 2? Not a problem. In fact, if we can sub in directly, let's sub in. That's why this is kind of a quick problem. If x were to take on the value pi over 2, what would the cosine be?
0.
0. And down here, we've already decided it's never going to be a problem. 3 minus the sine of pi over 2. 3 minus 1, so 2. So our answer is 0. So some things appear that they might have a bad value, but in reality they don't. Have a nice, safe weekend, and I will see you hopefully on Monday.